All right, so now we're going to look at section 1.8, subsets of real numbers. So a subset is a smaller group of something that is contained within something bigger. That's a real kind of quick, dirty explanation, but that's what it means. A subset is some smaller group contained within a bigger group. So the natural numbers are our first and most natural place to start with subsets of real numbers. The natural numbers start with 1 and they go up from there. And these are probably the first numbers that people used, but eventually they decided, hey, we need 0. So we moved from what we call the natural numbers to the whole numbers. And so the whole numbers start with 0 and then go into all the positive numbers. Notice nothing negative here with the natural numbers or the whole numbers. For the integers, we're looking at all the positive and negative numbers, but only the nice ones. No fractions. And so I know that this is still a pretty happy place for a lot of people. They're like, okay, don't like the negative signs, but at least there aren't any fractions. Yeah, well, we're going to run that. Next up, rational numbers. There you go. There's your fractions. So if you're one of the many, many people out there who loathe fractions, I'm sorry, these are not your thing. Rational numbers are anything that could be written as a fraction. Now, that's going to include, obviously, fractions, but it's also going to include numbers like 2, because 2 could be written as a fraction if you just write it as 2 over 1. So we can take any nice normal looking number, put it over 1, and you have a fraction. It's also going to include terminating and repeating decimals. Terminating decimals are decimals that come to an end. Think something like 0.3. Repeating decimals have a pattern that repeats itself over and over and over again. Trust me, it's possible to turn them into a fraction. It does require more algebra than we have right here at this point, though. Irrational numbers, these are the really weird ones. The most common one that we think of is probably pi. You might hear, hey, pi, 3.14. Yeah, not exactly. Pi is this really fun number that goes on for actually literally forever, and it never forms a pattern. And that's what it means to be an irrational number. The decimal places go on forever, never forms a pattern. Now, all of these things together combine to make what we call the real numbers. Okay, so the real numbers are all of these different things. And so you're going to see some problems in your homework here where you have to try and say what kind, pick out all the real numbers or all the rational numbers out of a list of numbers. And so these are your different kinds of numbers that you're going to be working with. All right, so we're going to look at some other things that we can do with subsets of numbers. And so give me a second to change my board and we'll do that. All right, so continuing on with kinds of numbers, prime and composite numbers. These are two sets of numbers that we're going to find to have some value. Prime numbers are defined to be anything that is only divisible by 1 in itself. Some examples include 2, 3, 5, and 7. There are lots more. Okay, there are actually an infinite number of prime numbers. They go on forever. You can always find more. But if you look at the numbers on my list, what they have in common is that the only thing you can divide them by is 1 and that actual number. So for instance, with 5, you can't find anything other than 1 and 5 that will evenly divide 5. Composite numbers are that they're divisible by more than 1 in itself. So something like 8 is clearly divisible by 2. That's why it gets on this list over here with the composite numbers. One thing to notice is that there's only one even prime number, and that's 2. 2 is the only even prime number. And if you think about it, it makes sense. All your even numbers are going to be divisible by 2. So they all fall into the composite numbers except for 2 itself. All right, so now we're going to take a look at something called factor trees on the next board and prime factorizations. So we'll be making use more of the prime numbers. All right, so continuing with prime numbers, a prime factorization. A prime factorization is a unique way, or I'm sorry, I shouldn't even say a unique way. It is the unique way of writing a number as a product of prime numbers. And so the easiest way that I have found to get a prime factorization is to make a factor tree, what's called a factor tree. So I have an example here that I'm going to kind of walk you through here with the number 72. So what we're going to do is we're going to keep breaking our number up into numbers that will multiply to be that number. So with 72, I started with 8 and 9. 8 times 9 is 72. Sorry about that. I got got interrupted in the making of this video, so I'm just going to continue though. All right, so I have 72. I chose 8 times 9 because 8 times 9 is 72. The beautiful thing is, as long as you pick a pair of numbers that multiplies to be the one up above it, you can't do this wrong. Okay, you could choose 6 and 12. 2 times 36 would be 72, but it doesn't matter what pair you choose, as long as they multiply together to be the number up above. So I chose 8 and 9. Now 8 is not a prime number, so I split it up again into 2 times 4. I'm going to continue down this side, and I'll come to the 9 in just a second. So I did 2 times 4. 2 is a prime number. You'll notice I circled the 2, and I really like to do that because it makes it easy for me to see where my prime numbers are. Otherwise, I tend to lose them somewhere in my factor tree. But 4 splits up into 2 times 2, so you'll see I've now circled 3 2's. Come over to the 9. 9 is 3 times 3. Those are both prime numbers, so they get circled. And so what we can say is that 72 is equal to 2 times 2 times 2 times 3 times 3. Whew, that's a lot of numbers. And if you multiply it out, it works. And it's the only set of prime numbers that will multiply to be 72. Now, you could also write this with exponents. We had 3 2's, so you could have 2 to the third and 2 3's, 3 to the second. I don't care which way you write it, but if you're looking in the back of the book, I think it uses exponents. So that's factor trees. And yeah, that's basically this section. So good luck with the homework, and yeah, have a good day.